Okay, so intuitively, we say a function, graph it with lifting our pen off the page, like this one right here. This one, we would have to jump over the asymptote, so we've got a discontinuity. We say it's an infinite discontinuity, and that will happen every time you have a vertical asymptote. When your left-hand limit or your right-hand limit are equal to positive or negative infinity, you've got an infinite discontinuity. This one here is called a jump discontinuity. Because the function jumps from one value to another. So we will have a jump discontinuity when our left-hand limit does not equal our right-hand limit. Note, both of these limits exist, they just don't equal each other. Okay, for this one, so if C is our number, then f at C is defined. It's right there. The limit as x approaches C from the left and from the right exists. The problem is that that limit is not equal to the value of the function at A. And when that happens, we call this a removable discontinuity. So that is the left-hand limit is equal to the right-hand limit, but that does not equal the function at the point that you're talking about. Doesn't equal the function at A. Okay, when you have piecewise defined functions, you're going to have to look at what happens at all of the endpoints of their domains. Where are each of these following functions discontinuous? So let me write this one out again. F at x is equal to x squared x minus 2. Let's write that in factored form. What multiplies to negative 2 and adds to negative 1? So that's x minus 2 x plus 1. That pen is dying. And in the denominator, we have x minus 2. Okay, so we have common factors, and they cancel. We know that the domain for this function is that x 2. But once we've factored and canceled, we got our function equal to x plus 1, which we don't look like. It just looks like a line with a y-intercept at 1 and a slope at 1. Except that when x is equal to 2, we have a y value of 1, 2, 3. We would have a hole in our line. So we've got this line right here. Okay, and then a removable discontinuity. Where does it occur? When x is 2, what's y? There we go. Okay, we did this twice, right? What's the point of discontinuity? It's removable because the left-hand limit and the right-hand limit are the x is piecewise defined. It's equal to 1 over x. As x isn't 0, and when x is 0, be 1. Can you give me a quick sketch of what this graph would? Well, 1 over x, we'll do a little t-chart in our head. If x is 1, where 1 over 1 is 1. If x is 2, square and 1 over 4 is a quarter, and you can see that as x bigger and bigger, my function closer and closer to 0. And if x were a half the reciprocal, and I get 4. 1, 2, 3. And so you can see that as x gets closer and closer to 0, bigger and bigger and bigger. Square. The same thing happens over on this side. If x is negative 1 squared is 1, and 1 over 1. If x is negative 2 squared and 1 over 4 will give me a quarter. And I could say this with x being negative a half, squaring it, taking the etc. Okay, so that's what that function looks like. Piece when x is 0, y is 1. Of course, that's not continuous, because what is the limit as approach 0 from the left to this function? As we approach 0 from the left, this is going to positive infinity. As approach 0 from the right, I'm going to just put a plus or minus there, positive infinity. So my left-hand limit equals my right limit, but that limit is not a finite. We would say that that limit does not exist. Then discontinuity. Okay, although my left-hand limit equals my right-hand limit is equal to infinity, it does not equal the function 0. In any event, this is what makes it discontinuous. Could you turn to page 133 in your textbook and do questions